Calc 1, we're looking at section 5.3, the fundamental theorem of calculus. It's finally here. We get to see what is a fundamental theorem of calculus. Okay, just like we had the fundamental theorem of algebra, we get the fundamental theorem of calculus, kind of leading us towards where we're going with everything. So, if we start thinking about this function, we look at the area function equals, so the area of x. Okay, so area of a function based off x equals the integral from a to x of f of t dt. Once again, where we have the independent variables of the area function x, and then we talk about the variable of integration. Once again, this is just a dummy variable, this t that's in here. It's not actually talking about time. Okay, what we start recognizing, that we have this nice definition. Okay. So this definition says, let f be continuous for the function for t greater than a. The area function of f with left endpoint a is given by the area equals the integral from a to x of f of t dt. Once again, where x is greater than a, so a is the lower bound, x is going to be some upper bound. The area of the function is the net area. Net area. It's underlined right here. Stress that. Not total area, net area of the region bounded by the graph of f and the t-axis. Okay, once again, because x is kind of our input variable in here, that's why we aren't using the x as our differentiable part in there. Considering what's going on with everything within here, do realize that now we won't necessarily have triangles. We could have like this trapezoidal shapes, okay? We could have other values that go into this, okay? We could have more abstract shapes overall. So, the fundamental theorem of calculus. Now, this has a lot of things, a lot of different values, different interpretations that kind of go with it. Once again, depends upon where we're at and what we're thinking about within the function itself. Okay, so we're suggesting that the area function a for a linear f is the antiderivative of f. That is, f prime of x equals, or I'm sorry, a prime of x equals f of x. So we have to think about this as that antiderivative of what we're going through things. So we see that the area right here, they kind of start explaining it. And this is where they start kind of walking through this procedure on why things are going and how they're starting to be defined. Let's jump over to our theorems over here, and we can kind of see maybe a little bit better. Okay. So we see that we have the fundamental theorem of calculus. Once again, if f is continuous on the interval from a to b, the area of the function, so the area function equals the integral from a to x of f t dt, once again, where we're going a less than or equal to x less than or equal to b. If is continuous and differentiable, the area function satisfies this other equation down here. Okay, so we see that a prime of x equals the derivative with respect to x of the integral of a to x f of t dt, which equals f of x. Okay, so we're saying that the derivative of this area function is being related to the actual function itself within here. Okay, so which means that the area function of f is the antiderivative of f. Okay, so they go through this theorem. You can read through this. You can read through kind of what they're going through, what they're doing. But here is the big picture. Okay, here is what you've been waiting for in that last section, how you had to horribly work through some problems. I mean, the summation one, the limit as n goes to infinity of the summations, all the work, all the interpretation in there is now out the window because we get this wonderful theorem that helps us. Okay, so we start talking about if f is a continuous function on the interval from a to b, and cap f is any antiderivative of f on this interval, then the integral from a to b of f of x dx equals the antiderivative of this function. So the integral of this function f of b minus f of a. Okay, a lot of times we see it written this way. Okay, we see that we're going to take this integral of our function. So we're going to take the antiderivative of this function, and that's what that cap f of x is. And then we're going to evaluate it from a to b, but what we're going to do is we're going to plug the value in for b first into this function, and then minus off what the value of that a is. And boy, does this allow us to work with more abstract shapes, things that we can't possibly picture the area on here and work with. Now, do realize, like everything else, just kind of coming over here, it is the net area, okay? So if we have a graph where it's above the x-axis and below the net x-axis, if we're finding net area, once again, the fundamental theorem of calculus is going to give us the net area for this. But if our problem's asking us for total area on this, that's when we got to break it apart, and as in the previous sections, into looking at this positive area minus then. So we got to do the definite integral on this part and then minus the definite integral on this part. We actually got to break it into parts. So realize that things could be tricky in setting the problem up, but overall, this nice theorem will allow us to work through the problems 10 times faster.